All right. Thanks everyone for joining me today. So I'm going to give you a whirlwind tour of how we do direct imaging and how we obtain spectra and what's the current kind of state of the art in obtaining spectra with direct imaging. All right, so let's get started. So just to set the context, there's not, as you saw yesterday, we don't have very many planets detected through direct imaging. And that's because direct imaging of exoplanets is very challenging. To give you an analogy, for the easiest directly imaged exoplanets that we can detect today, it's analogous to trying to watch a firefly circle a streetlight, which gives you a sense for the brightness ratio between the planet and the star. And trying to watch that firefly circle a streetlight from several miles away, which gives you a sense of the angular separations we're trying to discern such a faint object from the bright glare of its star. So how do we do this? So this is a cartoon I drew of how we image an exoplanet. So this, we're not doing optics at this Sagan workshop. So this is how deep we're gonna go. We're good? All right. So as you saw yesterday from Heather's talk, direct imaging is mainly only sensitive right now to Jovian exoplanets. So all the spectra you'll see in this talk are gas giant exoplanets, the mass of Jupiter and higher. So we try to image these planets next to their bright stars. Generally, we do this from the ground, although now more and more we have more space-based spectra of exoplanets, but oftentimes we do this from the ground. So atmospheric turbulence, oh, I can't stand away, I have a pointer. Atmospheric turbulence gets in the way. So what we have to do is we have to use a technique called adaptive optics to correct for atmospheric turbulence. It's literally like going to an optometrist for a telescope, but we're doing it every millisecond instead of once a year like we all should. And then we use some technology to suppress the glare of the star in order for us to image exoplanets. I'll just give you a couple slides just to appreciate how all this technology works. So this is an image of the star from the ground without adaptive optics. Normally you see it like a dot, but if you were to magnify the image and zoom in, this is what the star will look like. This is what's called a seeing halo. This is all the atmosphere blurring the image of a star. And then once we turn on adaptive optics, you can see we go from that to that. So we're able to concentrate the light, all this light into a central core. We get about a factor of 20 or 30 increase in spatial resolution by doing this. And if you're looking at this image very closely, you'll actually notice there's actually a second point source in this image. This is a binary star system. This is a low mass star orbiting another star. And this second fainter star will be completely lost under the seeing halo without adaptive optics. And this is just a star. This is a binary star system. Planets are many times fainter than this. So I think it'll be even harder to image planets without adaptive optics. So adaptive optics from the ground is key. And even in space, you'll probably hear on Friday, we'll need some form of adaptive optics for space-based exoplanet imaging. But even with perfect adaptive optics, let's say we launched a circular telescope into space and image a star. There's no atmosphere, there's no turbulence. This is what the image of the star will look like. And this is actually a simulation we made with a star and a planet. But you can't see the planet at all because these planets, even with perfect adaptive optics, with perfect wavefronts, are hidden under the diffraction of the star. So just to the pure quantum nature of light, the star interferes with itself, creates these diffraction ripples, and any faint planets we're trying to see are completely hidden underneath the diffraction ripples. So we have to use optics called coronagraphs or similar starlight suppression techniques to basically block out and suppress the diffraction of the star so that we can actually see the planet. So there's actually a planet simulated in both images, but without putting in the coronagraph, we would never have seen the planet. So this is ideally how things work, but nothing ever works perfectly. So we also have to do additional post-processing generally to separate out the residual glare of the star from the planet signal. So here is one of the techniques we use to do that. You'll probably hear about more of these on Friday in the James Webb's talk. From the ground, we often use a technique called angular differential imaging. And this employs the fact that the Earth rotates. So basically the sky rotates. So have you ever seen those night sky images where the Milky Way is rotating across the night sky? We're taking advantage of that fact. So all the stuff you're seeing here is stellar diffraction, except for this one dot. That is actually a directly imaged exoplanet. That's Beta Pictoris b. And this is not orbital motion you're seeing. This is due to the Earth's rotation that it's orbiting apparently in our image. And using this technique, we can distinguish what patterns are due to diffracted starlight, which remains static over time, versus what is an astrophysical source, which moves as a function of time. And then we use sophisticated signal processing algorithms. The state of the art in the field is principal component analysis, and we basically reconstructed the diffraction pattern of the star. So here is an animation seeing how this all works. Again, we're not diving into the details. This gives you a qualitative picture of how everything works. So on the top left, this is the data. This is almost everything you're seeing is the diffraction pattern of the star. On our right is our principal component reconstruction of that image. And it's actually an animation. We're adding more and more principal components to represent more and more of the structure of the image. But you don't really notice that in the top two panels here. Once we do a data minus model and look at the residuals, you'll see that as we add in more and more principal component modes, we actually subtract off more and more of the diffraction pattern of the star. And you can see that we're removing more and more of the structure that we see in this image. And then we stack 55 of these images together. You'll see that actually, as we increase the number of principal component modes to remove more and more of the substructure, we actually get this faint point source that appears right next to the star. This is actually a real astrophysical point source. Turns out this is a chance alignment with a background star that just happens to be 0.2 arc seconds away from the star we're interested in imaging. So this is not a real planet, but it gives you a sense for how we actually detect faint planets next to very bright stars. And there's a lot of different algorithms. I wrote an open source package called PyClip, but there's also many other packages and algorithms written in the field about how we can do these kind of techniques. Okay, so after we're able to do that, we can then get images of exoplanets. This has been pretty cool. And in fact, if we take many images over time, we can actually watch these planets move. This is not the purpose of this workshop, but you can take a moment to admire. So these are 4 planets orbiting HR 8799. This is a 12-year time lapse over here. You can watch them in motion. This is a 17-year time lapse of the Beta Pictoris b system. It's probably the longest time lapse we have of any directly imaged exoplanet system. It's on a near edge on orbit, and you can see it orbit on this near edge on orbit relative to the star. All right, once we have these images, we can start imaging these planets at different wavelengths, and you can measure the brightness of these planets at different wavelengths. And what this tells us, this gives us the first glimpse of what these planets are made out of. So that's what happened in the very beginning of direct imaging. We started measuring the photometry of some of these planets. So this is the brightness of these planets on the y-axis as a function of wavelengths. Each of these points is the measured brightness of the planet at each of these black points is the measured brightness of the planet at various bands. And what you'll notice, especially here at 4.7 microns in the M band, this planet HR 8799c is quite faint at these bands. And because it's quite faint at these bands, we know that there's carbon monoxide absorption at this particular wavelength. So looking at the brightness of these planets at particular bands of interest gives us the first glimpse of what kind of species are in these planets' atmospheres. But we're in a spectroscopy workshop, so we want to move just beyond just photometry. So for the rest of this talk, I'll talk about how we do direct imaging spectroscopy. And we do that first with integral field spectroscopy. So integral field spectroscopy combines the best of imaging and spectroscopy. Basically, every pixel on our detector is dispersed into a spectrum. We can get a spectrum of every single pixel. And you can see there's a whole suite of kind of this state-of-the-art exoplanet imaging instruments: Gemini Planet Imager, VLT Sphere, Subaru Skexio Keras. They're all integral field spectrographs where we can take both images and spectra simultaneously of these gas giant exoplanets in the near infrared. So here's what some of these images look like. So this is a integral field spectrograph in the H band, about 1.6 microns of 51 Eridani b. The planet is right here. And you can see that there's both water and methane absorption in this planet. So when the planet atmosphere is absorbed by both water and methane, the planet is very faint. And then in between these two opacity bands, when there's no absorption, you can see the planet peak up in brightness. And this is how we can, basically we have images at 37 different wavelengths, and this is how we're able to obtain the low resolution R about 50. So this is lambda over delta lambda, telling you how fine our wavelength sampling is. We can observe these broad molecular absorption bands to give us a sense for what the composition of these planets are. So with that, we're able to actually obtain spectral libraries of low resolution spectra. So this is what's been done with the Gemini planet imager. These are both brown dwarf companions and directly imaged planets. And we generally have done this all in the near infrared. So this is spanning from 1 to 2.4 microns. You'll see absorption by things like water. So these are water absorption bands you see here. This is another water absorption band you see right here. You can see there are common spectral features between many of the planets. There's carbon monoxide absorption here at about 2.3 microns. You can see they all kind of dip down. And then for the coolest planets, notice they're sorted by temperature, effective temperature. When we go down to really cool planets, about 700 Kelvin, we also see methane absorption in these planets' atmosphere. So using this, we're able to detect these molecular bands telling us about the temperatures and the broad properties. So with this, we're able to, with these low resolution spectra, we're able to obtain constraints on the bulk properties of these planets, the temperature, surface gravity, and radius to about 10% or so. So here is Beta Pictoris b, one of the planets you saw previously. These are the IFS spectra of the planets, and then in the blue and the red are model fits. And you'll notice that the models don't always fit pretty well, which is probably a common theme of this entire workshop. And what we found is that once we started obtaining these low resolution spectra at multiple wavelengths, these models, these data show systematic disagreements with models that, especially in the how bright things peak in the J band relative to H band and things like that. And getting this right is very difficult. So that's some stuff we're still working on. One of the issues, in addition to the model disagreement, is we also deal with correlated noise in our data. So some things like this, we don't think are real, but due to residual starlight in our images, it creates this correlated noise that is hard for us to remove. And this has been one of the limitations of integral field spectroscopy spectra so far. And because of this, because both the data has some, we have limitations with the data and sensitivity to data systematics, precise compositional measurements using just low resolution spectra have been difficult. So this is again 51 Eri b, this planet you saw with methane and water absorption in its atmosphere. And these are two different studies, all published this year, trying to measure the carbon, the C to O ratio, and the metallicity, the Fe over H of this planet. And these two papers use different models and use different subsets of data. And you'll see that the carbon to oxygen ratios are quite different. And the metallicities also have this very broad uncertainty going from solar metallicity at 0 to very much supersolar. And it's hard to distinguish and have confidence in the compositions constrained from these low resolution measurements, both because the model and the data have issues. So that's stuff we're still working on. But luckily we have there are ways to get better low res spectra, and one of them is using optical interferometry. So we'll hear more about interferometry later, but right now the state of the art, kind of before JWST, some of the best spectra ever obtained of a exoplanet was done using optical interferometry with the gravity interferometer at the VLT. Here, this is again Beta Pictoris b, and you can see this very precise spectra, and in particular, you can see individual CO absorption bands detected in the data. And the nice part about interferometry is that in addition to unlike imaging, it can also obtain information about the phase of light. So remember, you remember from your electricity and magnetism class, light has both intensity and phase. And by measuring this phase information, we can actually filter out the noise due to the glare of the star in ways that we can't do with just conventional imaging. And with this, we're able to obtain these better spectra. And you can see that we can measure much more precise carbon to oxygen ratios and metallicities down to the 5 to 10% precision level. And this is all done with the Petit Rat transcode, which you'll play with tomorrow. All right, so that's low res spectroscopy. We're now going to move to medium res spectroscopy with direct imaging. So medium res spectroscopy operates at a spectral resolution between about R of 1,000 to 10,000. At this resolution, we're resolving individual molecular absorption lines, but we're not resolving their line shapes. So we're seeing individual wiggles in the spectra, but we aren't measuring the shapes of each of those individual wiggles. With this, so you can see here, this is some of the pioneering work with this has been done with Keck Osiris. So you can see these are the molecular templates that folks are using. You can see for like carbon monoxide and water, these are the individual absorption lines we're trying to detect. And this is actually in red, the real data for one of the exoplanets. And you can see the dip here due to carbon monoxide detected in exoplanets. The original work for this has been done with Keck Osiris, also VLT Symphony, and these are generally integral field spectrographs as well. But because of the finite number of pixels you can have on a detector, we're generally trading out field of view for spectral resolution. So we have more pixels dedicated to spectral resolution, getting more precise spectra, more fine resolution spectra, and less pixels dedicated to getting more of the field of view. So you can see that these are very narrow field of view images. The star is somewhere way out here, and it basically just the planet is on the detector. And we used techniques to basically spectrally filter out the starlight to distinguish it from the planet. Because you can see here, the starlight has a completely different spectrum than what the planet has. So we're able to use that to distinguish the two. Just for the aficionados in the audience, there's kind of two ways that we can use to spectrally filter out the starlight. One of the ways, which you'll hear about, you'll probably hear about these a lot more in the high-res spectroscopy talks later today. So I'm not going to go into the details. One is using the cross-correlation technique. So here, each molecular template has a different spectral signature, and we cross-correlate it with the data. And basically, where there is a planet with actually that molecule in its atmosphere, we'll get a peak. And everywhere else, when there's just starlight, it will not correlate significantly, and basically, it will all average out to 0. Another way to do this is they're actually statistically very similar, but the approach is slightly different kind of philosophically, is using a forward modeling technique. So in the forward modeling technique, we're modeling both the starlight and the planet jointly. And instead of just cross-correlating a template against the data, we're doing a fit for both the stellar spectrum and the planet spectrum to the data itself. But using this technique, you can actually do the math and get an equivalent cross-correlation map as you can do with the standard cross-correlation technique. But it's a nice thing about this technique is that you're also able to fit the systematics and starlight in the data. Medium resolution has actually provided some extremely precise spectra, and it's been quite exciting to see some of these spectra coming out of medium resolution spectrographs. So here's an object we'll have you hear a lot more about in the JWST talk, VHS 1256b. You can see all these individual wiggles in the spectrum due to molecular signatures. The C to O ratios measured still have a broad range, but generally they're model limited now. So we're less limited by the quality of the data and limited by the fact that each model we use gives us a different interpretation for what the C to O ratio is. With these high quality medium resolution spectra, we're kind of hitting the limits of the models. But empirically, we're also able to do a lot. So here is another exoplanet image at medium resolution. This is with VLT Symphony. And you can not only, again, see the precise carbon monoxide bands, but if you look really closely, in addition to 12 CO, which is regular carbon monoxide, there's also signatures due to 13 CO. So this is an isotopolog. So the carbon in this carbon monoxide atom molecule has an additional neutron. And because of that, its molecular weight is different. And because of that, the transition lines are different. And we actually can detect the signature of 13 CO in the data using these high quality medium resolution spectra. So this is really exciting, and then it's going to get even more exciting with JWST. It has has medium resolution spectra both in the near infrared and mid infrared wavelengths. And I encourage you to see Aaron Carter's talk on Friday to learn more about that. All right, so that's medium resolution spectra. I'm gonna try to do. All right, so now we're going to talk about high resolution spectra last. So in high resolution spectra, in addition to observing each molecular absorption line, we're actually also spectrally resolving the line profiles. So this is an example of a high resolution spectra from a brown dwarf. This is not of an exoplanet. You'll see in a second why. But with these high resolution spectra, we can see these individual wiggles due to things like water and ammonia in the atmosphere. But in addition to that, we can also measure the line shape profiles. We can actually measure how broad this line is. We can measure the Doppler shift of this line. Because if the planet is moving towards us or away from us due to things like orbital motion, these lines will all get globally Doppler shifted, and having a high spectral resolution allows us to measure that Doppler shift. So not only can we measure the Doppler shifts of stars to detect planets, we can actually measure the Doppler shift of planets themselves. And this allows us to characterize the orbits of the planets. And now, additionally, folks have started to look for measuring the wobbles of these planets to look for moons around these planets. In addition to the rate of velocity, we can also measure the spin speeds of these planets. So if the planet is spinning, one side is spinning towards us and one side is spinning away from us. So one side is being blue shifted, one side is being redshifted. So as this planet spins, you can imagine this absorption line gets broader and broader as it spins faster and faster. So if you had so Paul talked about broadening absorption lines due to things like pressure broadening. Rotation broadening is another way that we can broaden the absorption lines in the spectra of these atmospheres. And for the directly imaged planets, the rotation broadening generally dominates the broadening of these lines that we detect. So planets are very faint, as we've seen. And if you're dispersing a planet at very high spectral resolution, say you're dispersing the light of the planet across 10,000 spectral channels, there's not very many planet photons per spectral channel. So here's actually a high-res spectra of a directly imaged planet. In black is the data. And the data, we've actually done a forward modeling techniques to model the data and the forward model can be decomposed of two components. There's the blue component, which is the residual starlight that's coming into our spectrograph. And in red is the planet spectra that we inferred. And so you can, and then in black, these black data points down here, this is the residuals of the data minus the model. You can see our residuals are pretty clean, but you can see that the planet light is within the noise. So because we're dispersing the planet across so many spectral channels, we get so few photons per channel that you often cannot look with the current 10-meter class telescopes. We can't see individual spectral absorption lines in the planet. Any individual line is at a signal to noise of 1 or so. And we have to use the combination of all these lines together to make inferences on the planet's atmospheric properties. There's been a lot of work on this front, and you'll probably hear more and more news about this as we go. There's actually several posters at this workshop about high-res spectroscopy that I encourage you to check out. So traditionally, high-res spectroscopy of directly imaged planets, the first high-res spectra done of directly imaged exoplanets, have been done with adaptive optics assisted high-res spectrographs using slits. So you basically place your slit somewhere on the planet, and you find that planet in your slit using something like cross correlation and detect the planet that way. This has been done with both VLT CRIRES and Keck NIRSPEC. The problem is that, as you can see, this is a real image of a star containing multiple planets. The star is very bright, and you have to filter out all of this starlight to look for the planet in your data, which is very difficult. So we've now been developing new exoplanet focused high-res spectrographs that use what's called single mode fibers. Single mode fibers are, I'll just briefly mention that there are cylindrical waveguides, and if that brings you something about ENM, we'll just move on. These single mode fibers have very small apertures on the sky, meaning that we can place one exactly at the location of a planet to couple in only starlight at the location of the planet, rather than coupling starlight across the entire slit. And there's been many new spectrographs being built to do this. So you see posters here on about Keck and KPIC. There's also VLT HiRISE and Subaru Reach, all doing this single mode fiber fed spectrograph for exoplanet high-res spectroscopy. Just like medium resolution, there's two kind of ways in the data analysis to detect planets. One is using cross correlation. This is what's been done for the first planet detected at high-res spectroscopy. So this is Beta Pictoris B. The slit was actually placed along the axis with the star. That you can see that using a planet template, the star completely disappears in the cross correlation, and only when the planet is aligned, when you cross correlate at the location of the planet, you get a peak in the cross correlation. The Doppler shift from 0 allows us to measure the velocity of the planet, and measuring this width of this cross correlation signal allows us to measure the spin speed of the planet. So this is the first time we were able to measure the spin speed of a directly imaged planet. And now you see that here in this talk and also in some posters, we're now doing also forward modeling techniques where we forward model both the starlight contribution and the planet light together to fit the data jointly in a regular likelihood framework. What have we learned from high-res spectroscopy? One thing we can do is measure what's called V sin I. So I would say we can measure the spin speed, but there's a caveat. We can only measure the line of sight projected spin speed. So it's the spin speed times the sine of the inclination angle. So we have to assume something about sine of the inclination angle. But as long as we can assume something about that, we've found several interesting results. One is that we've, again, proven the conservation of angular momentum. So planets start out puffy, and as they cool over time, they'll contract to smaller and smaller radii. And what we found is that planets' spin speeds generally increase as they contract, following angular momentum conservation. But additionally, regardless of age, all right, I'm almost done. Regardless of age, we've detected, we see planets are generally spinning at about 10% of breakup speed. So this is consistent with the picture of magnetic braking at early times. With high-res spectroscopy, we're able to measure spectra of planets that are independent of our choice of cloud parameterization. So we can measure things like the carbon to a hydrogen ratio, and depending on whether we use different cloud models or even a clear model, we're able to obtain the same C/O ratio and metallicity, because we're able to probe these cores of these lines that form well above the pressure levels where the clouds exist. Composition measurements are still the beginning. Sorry, I'm running out of time. So I was going to put this up. The future is bright for exoplanet imaging. There's a lot of cool stuff happening. I'm happy to take any questions. Thanks.
All right, we have well, maybe 2 minutes for quick questions. Tom?
I'll combine these. So early on, you showed the 51 Area B, even though the signal really varied a lot over the H-band, it looked like the error bars are the same. So what's dominating the noise? Is that speckle noise? Is because it didn't look like it was photon noise from the planet? And the second one is, can you go down to first order for single mode fibers and their advantages? Because to zeroth order, it seems to me, versus a slit, you're going to have the same amount of starlight over the same spatial element that the planet subtends, and the rest of it should be in the background. So if you could,
yeah, for your
or tell me whether this is something
I have answered. Yeah, so for the first question, for 51 Area B, the error bars are constant as a function of wavelengths because we're limited by speckle noise, which is generally wavelength independent across a narrow band. So that's why the error bars are all the same. For your second question about single mode fibers, in addition to their smaller size, do they provide additional starlight suppression? The answer is yes. It's because they're a cylindrical waveguide that only accepts the first special mode function. So if you remember your electricity and magnetism about cylindrical waveguides, it turns out the speckle field, electric field, does not have very much power in that first special mode function. So you actually gain additional factor of 3 or so in starlight suppression inherently due to the single mode nature of the cylindrical waveguide we're using.
Hi, Mara Benjikchi. I'm a grad student at Arizona State University. You talked about how there's disagreement with the models for the J, H, and K bands. Do you have a sense for why there is not agreement between the different bands? And is that something where we should be modeling the bands separately, not all as one model?
Yeah, so the question about fitting all the bands together is hard, and what should we be measuring them separately? Perhaps we should be fitting them separately. I'm not sure. The age-old thing to blame is clouds, but I'm not sure I know the answer. Maybe the modelers can speak up about why we can't fit all the bands at the same time.
Do we have time for one online question? Okay. So there's a question online asking, is it plausible to discover planets within a brown dwarf binary companion system, despite the ultra cool nature of brown dwarfs using direct imaging method? And what are the challenges?
So can we detect planets around brown dwarf binaries? Well, I don't see why not. We've detected planets around brown dwarfs. One of the first planetary mass companions to ever directly imaged is 2MASS 1207b, which was discovered around a brown dwarf. So why not brown dwarf binaries?
All right, I guess we can continue the question online, and let's thank Jason again.